Hello, my name is Daniel Mitchum. I'm the electrical sub-team lead here at the North Carolina State University Underwater Robotics Club. I'm a senior in electrical and computer engineering. And here's the rest of my team.
My name is Isaac. I'm a sophomore majoring in electrical engineering.
My name is Justin. I'm also a sophomore in electrical engineering.
My name is Dheeraj, and I'm also a sophomore in electrical and computer engineering.
Hi, I'm Byron Chi, and I am a second-year computer and electrical engineer.
Marcus Beal. I am a sophomore in computer engineering.
Hello, my name is Cody Jefferson. I am the standing mechanical team lead of the NC State Underwater Robotics program and currently a senior studying mechanical engineering.
Hi, my name is Jeremy Hosang, and I'm the vice president of the Underwater Robotics Club, and I'm also studying mechanical engineering.
Hi, my name is Gabriel Shinver. I'm a junior in mechanical engineering at NC State.
Hi, I'm Nolan Kenigallo. I'm a junior in aerospace engineering at NC State.
Hi, my name is Samarth Patel. I am a biomedical engineering junior.
Hi, my name is Amal Nayangar. I'm the club president and software lead, and I'm a graduate student in electrical engineering.
Hi, my name is Amr Musa. I am a sophomore in computer science.
Hi, I'm Henry Sneed, and I'm a sophomore in computer science.
Hey, my name is Harshal Suthar. I'm also a sophomore in computer science.
Hi, my name is Tadja Trappier. I am a junior in materials engineering with a concentration of nanomaterials.
I'm Cameron Incy, and I'm a sophomore in computer science.
Hi everyone, my name is Shannon Pinnell. I am a junior studying electrical engineering and I was the acoustics lead this year. And with that, on to the rest of the acoustics team to introduce themselves.
I'm Justin Otakowski and I'm a junior in electrical engineering.
And hi, I'm Chloe Haas. I'm a sophomore in electrical engineering.
Hi, I'm Chris Morey. I'm a junior studying electrical engineering.
We're the NC State Underwater Robotics Club. We have 25 members split across 4 sub-teams, and we focus on both the RoboSub competition and the academic and professional development of our students. This year we have multiple funded research projects in the College of Engineering in the field of underwater vehicles. We're very excited to show our new robot this year, SeaWolf VIII. This is a completely new design that's a major departure from previous iterations. We built it with a focus on robust electronics and the creation of a stable platform for advancing our missions. We successfully tested manual control of this in early March, and since then have redesigned the software in ROS. This year, since we are going with a completely new frame, we have a more conservative strategy with only navigational tasks. We are going for the same tasks we attempted at RoboSub 2018. We have fairly high confidence there, as well as a stretch goal of surfacing in the octagon. We can reuse our past computer vision code and have created new computer vision neural networks for the octagon and buoys tasks.
Because our electrical team has been a recent cause for team-wide slowdowns, the approach taken with the design of SeaWolf VIII's electrical system focused on creating a stable platform from which more custom and experimental projects could take root. In the past, using a nearly completely in-house designed system resulted in issues with causes ranging from inadequate design to overly complex circuitry. In stark contrast with the previous SeaWolf design, SeaWolf VIII features a multitude of off-the-shelf components supported with a few custom PCBs that handle some of our niche operations. The idea here is to reduce complexity, risk, and allow higher-risk projects to be point scorers rather than staple parts of the robot. SeaWolf VIII's electrical system, dubbed the MOAB, features 3 of our custom devices, those being the load balancing board, the opto-isolator board, and the main electronics board, or the MEB. These devices tie the rest of the system together, which can be seen in the block diagram of our system here. The MEB switches power to thrusters in the system, as well as handling communications with auxiliary devices. The load balancing board switches power to 2 parallel LiPo batteries, giving us more time to test in the water before having to recharge. The opto-isolator board optically isolates the thrusters from the system ground. The Pixhawk flight controller provides stabilization, telemetry, and thrusters controls via commands from the Jetson. It is through the Pixhawk and to the opto-isolator board that these commands are sent to the electronic speed controllers.
For a brief overview of the mechanical systems, I'll give a synopsis of some of our design features. Some of these features are ones that we decided to keep from SeaWolf VII, others of ones that we improved upon. Some of our novel features include our modularity. As you can see from the rendering on the right, the frame of our robot has holes throughout it. This allows for the ease of attaching and changing our peripherals depending on the mission we're running. We also updated our robot to increase its platform stability. The goal was to create a platform that will be usable for the coming years. And if you look at our robot from the top, it has an octagonal shape. This is to allow for our new 8 thruster configuration, which will give us greater stability while moving, as well as greater strafe and yaw control. And lastly, we dramatically improved upon our system robustness. Our previous robot, SeaWolf VIII, had a frame that was comprised of laser-cut acrylic, whereas SeaWolf VIII has a frame that is made out of 6061 T6 alloy aluminum. This not only provides greater structural integrity, preventing parts from breaking, but the way our current frame is set up also prevents any external forces from acting on our electronics hull. Furthermore, we've improved our connections by swapping over to sealed bulkhead connectors.
The software team has upgraded our hardware to use a Jetson Nano with an onboard GPU for vision processing. It's also sufficiently low power and has enough communication peripherals to do everything we need to do. We're using ROS in Python and C++, and this interfaces with a Pixhawk and custom boards over a USB to UART link. There are a few major components of the software system. The first is the sensing. This takes input from the inertial measurement unit, the camera, the acoustic system to tell us where we are in space. This then gets fed into the mission that knows what we're looking for, whether it's the gate or the buoys or a pinger, and essentially has a state machine that says, this is what we were looking for now, we found it, let's move on to the next task, or let's circle back and try to find it again. As well as a controller that tries to close the loop between the sensing telling us where we are and the mission telling us where we want to be.
Broadly, the goal of the acoustics team is to calculate the position of the vehicle relative to the pinger. To do this, the team calculates the time difference of arrival of pings at 4 spaced hydrophones, then applies hardware filtering and amplification, and then applies an intersection of cones mathematical model. From this, the relative location of the pinger can be determined. In creating this data pipeline, iterative testing is a must. On the left side of the screen, a breadboard testing a new low-pass filter and amplification chip is shown. By isolating and testing a new component, the way that a component will fit into the broader system is more clear. Not shown are other breadboards that have multiple stages of the system which help contextualize how the different subsystems interact. Also not shown are perf boards created for in-water testing. These boards are less prone to noise and mechanical disconnection than breadboards, and are quicker to produce and less costly than PCBs. This gives the team flexibility to test and integrate the system unencumbered by PCB manufacturing schedules. Once this testing is complete, a PCB is created for more long-term use, and in the middle an Altium schematic of the system can be seen, which is then used to do place and route for the final PCB. On the right, a ping is captured during in-bucket testing. Due to both current world events and the setup of our campus, it can be difficult to have testing time in the pool. Using a large plastic tub filled with water helps us test the system as often as possible and ensures the system is working as expected even before entering the pool. The acoustics team has worked hard over the past year to customize our signal pipeline and incorporate more data-driven decisions into the design process. The mechanical team installing new brushless thrusters was exciting, however it quickly became evident that a switching frequency of about 18 kHz was too close to comfort for our frequencies of interest on acoustics and could be a large source of error. After bucket testing a thruster in the water with a hydrophone and pinger, it was clear something needed to be done. In response, a custom 4th-order high-pass filter was made and a bucket tested. This yielded much cleaner results and was eventually, after more simulation and testing, made part of our PCB. I mentioned earlier that pool time can be difficult to get due to the layout of our campus, but it can also be difficult to get once in the pool and be able to have enough time to fully test the acoustic system while being respectful of other sub-teams' time for testing. To remedy this, we used a leftover shell of SeaWolf VII, which still had a hull and a hydrophone mounts on board. However, there were no electronics. To test, we created perf boards that were able to run a full set of hydrophones off a few 9-volt batteries. This made us independent of other subsystems for testing and allowed more testing to be done as a whole during our time in the pool. Additionally, we moved to a more simulation-based model. Simulating new subsystems and LT spice has become the norm, allowing us to detect errors before purchasing parts to breadboard with. The first picture in the middle of this slide shows our high-pass and amplification circuitry where we performed simulations prior to additional testing. In doing this, we realized some of our resistor values could be changed to give us more sensitivity and that we had a few capacitors that were unneeded.
FlatSub was born as a development platform for the SeaWolf VIII electronic system, where all components could be laid out, bolted down, and connected together, giving a clear visual of where and how things were connected. The idea behind this platform is that once our electrical system is proven and in place, implementation and testing of new aspects could be done on FlatSub, a one-to-one replica of our dedicated electrical system. FlatSub was utilized to test each component under load and failure conditions before integration into the robot, as well as to test our custom circuitry and safety switches under a full thruster load. This testing is what led to the design and implementation of the opto-isolator board upon realization that the ESCs became the return path for thruster power when they were switched off via the MEB. Once lab access was lost due to the pandemic, the team had to find new ways of verifying our designs. Utilizing LT-Spice, we could build and simulate our circuits with their inputs and outputs to verify that they would operate as intended, or test which components gave us the results we were looking for. In our case, the load balancing board was a prime candidate for this sort of simulation. Completely analog, yet difficult to understand unless you can see the signals drawn out for you, this board required LT-Spice's simulation and visualization tools in order for our team to understand and be confident that our design would operate as intended. Once we were confident in our testing, we pushed the design into Altium Designer for official schematic and PCB design.
For all of our mechanical components, we do extensive testing to ensure that everything works properly before incorporating it into the robots. For anything that needs to be waterproof, we hold multiple rounds of waterproof testing at various depths and for various durations to ensure that everything holds tightly before we put any electrical components in them. Unfortunately, after COVID-19, we lost access to our lab, so our development had to kind of change gears. We went from our usual process of developing multiple prototypes and iterating to improve our designs, and we switched to a more simulation and design optimization route. We utilized multiple tools inside SolidWorks, including static, dynamic, and fluid studies, in order to simulate the performance of some of our components before we even decided to fabricate them in the first place. On the right side of this slide, you can see some examples of some of our various torpedo shapes that we simulated using SolidWorks. This was necessary in order to continue being productive upon our robot development. Without access to our lab, we were not able to develop prototypes and iterate like we normally do, and this method allowed us to continue our production and make a successful platform for our robot.
Since most of our software development happened after work from home started, we moved all of our development to simulation with our existing pipeline of ROS, Gazebo, and Ardusub. We built up our control system in simulation. We standardized and containerized the environment with Docker, which allowed us to automatically unit test our functionality with continuous integration. So we can write tasks, make sure that the robot does what it's supposed to be doing, and make sure that happens whenever any change happens. So you can see in this video that when new code is pushed and it's tested, the robot is given a desired pose or place in space that it wants to be at. The robot will automatically try to move there, and an oracle will essentially decide, has it gotten there sufficiently? And this happens every time we push code. We also worked on improving our computer vision from home. So since we didn't have pool access, we had to get a little bit creative with this. So we actually took a bunch of pictures in bathtubs and sinks and in various lighting conditions outside at all kinds of day. And we worked on building traditional and neural network-based models for this that were, trained on this sort of simulated data. And when we get back to having pool access, we hope to, retrain these models on actual data, as well as build experience so that, when we have access to the data, we will be able to create successful computer vision models.
Without access to a lab space or pool for testing, the acoustics team was able to perform multiple simulations of the power and signal processing pipelines using LT-Spice. After these simulations were complete, we were able to ship breadboards and components to students who could then use their analog discovery devices to test these in-development aspects of the system and report back on what they had found. We also added new functionalities to existing PCB layouts based on the results of these analog discovery tests. This included the high-pass filter that I talked about earlier. And we were also able to use simulation to better understand environmental factors and impacts using MATLAB. So that would be the top and bottom reflection that I talked about earlier. We also began to improve our software data analysis pipeline using existing data that had been taken at previous pool tests. We also determined the feasibility of bathtub testing. Now, unfortunately, none of our bathtubs were quite the right geometry to get the data that we needed.